Hey everyone, and welcome back to another video in my algorithm and data structure series. Today we're going to be going over a pretty commonly asked interview question. It's actually categorized as hard on Leetcode, but today we're going to be merging k-sorted lists. Problem statement goes as follows. You are given an array of k linked lists named lists. Each linked list is sorted in ascending order. Basically what we want to do is merge all of the linked lists into one sorted linked list and return it. To give you guys more of an example, here we're given 3 linked lists, 1, 4, 5, 1, 3, 4, and 2 and 6. And what we want to be outputting is this kind of merged linked list sorted in ascending order. So this 1, 1, 2, 3, 4, 4, 5, 6. And a couple edge cases if we're passed in empty linked lists. So go ahead and pause the video right now and give yourself 5 minutes to think about potential solutions to this question. Cool. Well, I just opened up a whiteboard to help us better visualize the problem. So in this example, I'm going to be maybe just given a list 1, 2, 3. And how about another list 5 and 6? And of course, technically we could have up to k different linked lists. But let's just narrow or break the problem down into its simplest case with 2 linked lists. And this is actually very simple, similar to another interview question that's asked pretty frequently of merging just 2 linked lists. And probably the optimal solution here is either using 2 pointers. So I'll have a pointer here and a pointer here, basically taking a look at both elements. Whichever one is smaller, I'll append into this new list and basically increment the pointer if I use that element. So then I'd be looking at this 2, and again this 2 is less than the 5, so I can increment the 2, and I can keep going on. So obviously I'm going to be looking at each single iteration, basically of the time complexity, is going to be O of n, because I'm going to be looking at every single node up to the minimum amount of nodes in the list, because then I can just copy over the longer list. And then my space complexity here is just going to be O of n, with n being the number of nodes as well, because I'm going to have to append each new node into this result list or merged list right here. I believe there's also a way to do this in constant time if I just go ahead and choose. So I'll use this same exact example. If I have this initial array of this 1, 2, 3, I'll just redraw it actually. If I just choose the smallest element and kind of have that be my target list, so in this case this 1 is smaller than this 5, so I'll use this as kind of my main list, or it's going to represent my merged list. I can compare this element with my target element's next element. So this 2 and 5, right? If my next element in my merged list is less than my 5, I can just increment my pointer. So I'll be looking at this 2 and basically this 3 in the next iteration. Let's say, for example, this was a 3 though. And maybe I'll just make this a bit cleaner. Let's say this was a 3, 4, and let's say this was a 2. When I compare the 3 and the 2, obviously 2 is smaller than 3. 2 would actually get merged here. So I added 2 here, and basically 2.next would be equal to this 3 element right here. And then I would just increment again. So I'd be looking at this 3 next iteration and 6. So that way I can save on space because I'm not creating a whole new list to hold all my nodes. Cool. So obviously the problem gets a bit more complicated when we're keeping track of k lists, right? Technically, our solution we just came up with that worked for 2 lists would work for k lists. We would just have to keep track of k pointers, right? Coding that in an interview might be a bit tricky, and there's a lot of places where you could trip up, I think. So I would ideally like to come up with a cleaner solution here. Something that kind of just jumps out at me is that at any single point, Well, first off, right, every single element is going to be accounted for. So basically this 1, 2, 3, 4, 5 are guaranteed to show up in the merged list. At any single point, though, I really only care about the smallest element across all of the lists, because that's basically going to be the node I want to append to this new target. So one kind of brute force solution here, right, is I could just iterate or traverse every single list, create some sort of array to hold all my elements. So I'll iterate through here, get this 1, 2, 3, and then iterate through this list, 4, 5. I can just keep going k times and keep populating this array. And once that's populated, this is kind of a tail example because it's already sorted, but I would have to sort that array in n log time, n being the number of nodes. But basically, this sorted array would tell me the exact sequence in which I need to construct my node. So I'd have to have a 1, 2, 3, 4, 5, and that would be my merge list. I think in the event of an interview, this might be a cleaner solution just because it's easier to code. Our time complexity is this kind of n log n, right? Because we have to first iterate through n nodes, append everything to the array, sort it, and basically traverse the array again to kind of construct our new list. We drop these, and so the time complexity would just be n log n, and our space complexity would be linear, n being the number of nodes. Cool. So what we can do is kind of implement a heap here, because basically at any single point, we only care about the smallest element, right? So we could just keep appending elements in the heap, popping them out, and of course, because the heap gives us constant time in grabbing the smallest element, if it's a min heap. And basically that will be our node that we will append into this new list array until our heap runs out. I'm gonna jump into the code real quick, or maybe just do some pseudo code to hopefully better explain this. So our very first step in kind of our algorithm is constructing a heap structure. We want to iterate through each node in each list and basically append node.val into the heap. This is basically what's going to cost us that O of n space complexity. This is going to be n times k, k being the number of lists and being the number of nodes in each list. Easy way is just n being the number of total nodes. But once that's done, right, we can basically just keep popping from the heap as long as the length is greater than 0, and basically construct a new list based on the elements popped. And at the very end, we can just return head. And yeah, I think that should work. So why don't we go ahead and code this out so we can see what that would look like. We're going to need to import heap queue here, which just basically allows me to use some built-in helper methods that will replicate the behavior of a heap structure. So we can just say node heap, and we'll just initialize that to an empty array. And now we want to iterate through each list that's passed in and populate this node heap. I think the cleanest solution here might be just to create some sort of recursive helper method to traverse each list. And before I do that, I just want to check constraints real quick. And it looks like it won't exceed, or length won't exceed 10 to the 4th, or total length won't exceed 500, which is good to know because that tells me everything will fit. Basically all the recursive calls will fit inside the call stack. So we can kind of proceed with this recursion. So let's create a helper method. I'm going to say populate heap, and this is going to take in a node. Our base case here is if node does not exist. So if not node, we'll just return from the recursion. Otherwise, we're going to use the heap queue builder helper method here. So heap queue.heap push. I believe we pass in our heap structure. So in this case, it's going to be this node heap, and let's just initialize that before we call this helper function. So this node heap, pass that in as the first argument, and the second argument is basically the value. So that's going to be node.value. And basically, we can just recursively call populate heap again, this time with node.next. So basically, we'll just keep going until we don't have any more nodes, and our heap queue or our node heap should be fully populated. So we'll make sure to call that in each list. So for L in list, we'll call populate heap, passing in L, which should be the head node of each list. Just to make sure I'm on the right track, let's just print out our node heap at this point. Cool, looks like we have every single element in that heap. So then our next step is to keep popping from the heap as long as the length is greater than 0 and construct a new list based on the elements popped, making sure to return head at the very end. So the way I'll implement this, and actually before I get there, there's a possibility or an edge case right here that our heap is empty. For example, if our list was passed in like this or this, our heap would actually be empty. We don't really want to be popping elements from an empty heap. So why don't we just account for that base case here? So if length of our node heap is equal to 0, let's just return none. Or empty array. Not quite sure what they're looking for, but we can figure that out. Cool. So with that edge case kind of accounted for, let's just go ahead and start popping things from the heap and constructing our new list. So first thing I'll want to do is create 2 references to a new node. So we'll say list node and initialize that with our first element from the heap. So I can say heapq.heap push, and the argument here is going to be our actual heap structure, so node heap. And then we can say while node heap, the length of node heap is greater than 0. We want to construct a new node, so list node, and again, similar to line 30, we'll just heap push from our node heap. Basically, our temp.next is going to be equal to this new node, and then we can basically increment forward and set temp equals to temp.next. At the very end of this while loop, we should have an empty heap, which means all our elements are now accounted for in our merged list. We can just return our head reference to this initial node. Let's go ahead and run that. Heapq.heap push expected 2 arguments. Oh, sorry. So this is actually going to be heap pop. Cool. Looks like that passed that base case. Let's go ahead and submit this. Awesome. So there you go. Thanks for tuning in, and don't forget to subscribe.